Hey, welcome back to ViViMaT 2, the PhD sessions. Our closing speaker today is my colleague from TU Wien, Chia-Jui, or Ray as we call him. He's a tribologist and a PhD student doing research at both the Vienna University of Technology and the Saarlandes University. He has a background in both mechanical engineering and material science. His current study is focusing on surface engineering, particularly on laser surface texturing and characterization of anti-wear tribofilms. By now, I guess you know where the questions to the speakers go. Ray, you're up right after this short message.
Coatings is a peer-reviewed journal of coatings and surface engineering published online by MDPI on a monthly basis.
And now, laser surface texturing.
Hello everyone, welcome to my talk. My name is Chia-Jui. I'm a PhD student in Saarlandes University in Germany, and I'm now a research assistant in Technical University in Vienna as a cooperation that I can continue my PhD work. And firstly, I would like to thank Dr. Ada and Professor Kashot for the invitation that I can join ViViMaT. And today the topic, actually it is part of my PhD work. It is enhanced growth of ZDDP-based tribofilms under boundary lubrication by laser surface texturing. Basically, it is using laser surface texturing to try to enhance the ZDDP tribal layers. And before I go into the topic of laser surface texturing, I would like to start with the additives. Why using additives in motor oils? We all know that oils and lubricants, they have been commonly and widely used in the industry, but only good oil is not good enough. That's why scientists, they have put different types of additives into oils for different purposes and performances, such as anti-oxidation and viscosity index improvers. And of course, one of the most important one is the anti-wear performance. And when talk about the anti-wear performance, then we cannot ignore one of the most successful one is called the ZDDP. ZDDP has been used in the industry for more than 80 years. It was claimed that 2/3 manufacturer required to use it, and it is very powerful, promising to decrease wear and friction with some other extra functions like antioxidations and extreme pressure resistor. And one of the most important feature is that the price is lower than the other products. As we know now, until now here, ZDDP is very powerful, very commonly used, but we have to somehow nowadays to reduce the use of it. It is because of the environmental friendly issues and sustainabilities. As you can see here, from year to year, the use of phosphor and sulfur has been limited, and these limits actually open a new page of the study of ZDDP, because if you look at all the potential candidates that they want to replace the use of ZDDP, they are either now too expensive or the function is not as good as ZDDP is. So some researchers, they think that if we can understand how ZDDP is functioning on the surface, then we would be much closer to find a way to find out the replacement or alternatives of ZDDP. So what is ZDDP? Actually, you can see this is a typical ZDDP. It is a long-chain compound centered by zinc with sulfur and phosphor outside, and it is said in the literature that after a high temperature and high pressure rubbing, then a thin tribal layer would be formed on top of the surface. The thickness is normally lower than 150 nanometer, and the width can be from 100 nanometer to several micrometer. You can imagine it is island-like tribal layers on top of the surface, and the role of it is to be as a barrier between two surfaces that preventing direct metal-to-metal contact. And another function is it can collect those harmful wear debris and wear particles and prevent them to cause further damage on the surface. So in our study, you can find the experimental details here. In our study, this is how we generate the ZDDP tribal layer. That upper left here is a thrust roller bearing composed of an upper and the lower bearing washer, and the middle is a set of rollers, and we put the bearing set into the test ridge. It is called FE8 test ridge according to a German standard, that we apply the load and also oils and rotational speed. More details you can find out here. And the lubricant is we use mineral oil mixed with ZDDP additives. So when talking about making frictional test, we have to determine the lubrication condition, and by using the strip-back curve and also calculate by the Dawson-Hamrock calculation, then in the formula that we can see the case in our tribal test, the lambda ratio actually shows the lubrication condition is in boundary lubrication. And what is happening in the boundary lubrication is there is unpreventable wear within this lubrication regime, is because in boundary lubrication the oil film is not thick enough to separate the surface, so the contact happens. That's why wear happens, and the only method or the only way to prevent further damage is to have a tribofilm in between. So when a fully formed tribofilm is in between as a barrier, then we can have the ability to protect the surface. You can see the preliminary result that after tribal test we found fully formed tribofilm. You can see the color appearance is like blue and brown like layers, and we found out that after decreased rotational speed, then we can see that the color appearance gets less and less, and after a certain point the wear scratches and wear scars are starting to present on the surface, and we call this incomplete tribofilm. Then we can draw a line that is the boundary of the formation of protective tribofilm. We can see that above this line is the green region that the fully formed tribofilm can do its job to protect the surface, and beneath that it fails. And we can draw the line even longer, that in this plot the lambda ratio has been calculated, and the horizontal axis is the concentration of phosphor shown in ppm. And we can see that the green region is above, and also those failure region is beneath. And we will start thinking that is it possible that we can find a way to go into this red region. So we choose the 500 ppm of phosphor and slightly decrease the rotational speed to have a lambda ratio of 0.06, and we use laser surface texturing as a tool to make this approach. And yes, here the laser method I would like to show you is the direct laser interference patterning. We call that DLIP, because normally it is difficult to have a very fine structure with a very fast speed. But by using the DLIP, we could have a very good structure, relatively good structure with a very nice and fast speed. So you can see that here the laser get out from the laser source and then have a splitter split that into two sub-beams and then gather them again on top of the surface. And due to the coherence properties, then we can have an interference pattern. By modifying and adjusting the angle and the distance, then we can have, for example, line-like structure, dot-like structures, and more complex ones. And the idea to have these patterns on the surface is not, of course, not to damage it. Actually, we try to create some pockets on the surface, and when the contact is having the insufficient lubrication, then the oil and the lubricant in the pocket can go out and play the role. This is what we are going to do, and we'll be find out in the results part. And here are more details of the patterns that we created on the surface. So first is the dimple-like structures with a periodicity of 500 micron and also 200 micron. And then we create some cross-like patterns with a periodicity of 9 micron and 30 micron. Okay, here are the results that we can see. After laser surface texturing, we can see from the bearing ratio curve to see the surface profile that you can find out that when, for example, when we compare the cross patterns, then between cross 9 micron and cross 30 micron, then you can see that with a shorter periodicity, the larger influence by the age effects can be found. That also, it happens also with the dimples, that the red one with less periodicity has also a more pronounced age effect here can be found. And on the other hand, because the cross patterns change the surface more, actually, then you can see that the profile, the mean profile changed also more dramatically, that we can see the cross patterns provide larger volume for the oil storage. Actually, as we mentioned, that the laser surface texturing normally is providing the surface pockets to store oil and lubricants, and this is like a proof by using the surface profile parameters to describe the volume or the capability more precisely. And how about the wear, the frictional performance? As you can see here, this chart is the wear volume loss and also the mass loss. And we can see that in general, the laser surface texturing can decrease, or let's say reduce the wear from around 10 to 4, and even this one, the D cross 30, is tremendous low. As we can see that the laser surface texturing provide wear protection, and it is due to the capability of lubricant storage. But if you remember still that we mentioned in the boundary lubrication regime, the most decisive effect actually is whether we can have fully formed tribal layer on top of the surface. So that's why we would like to see further with the cross 30 if we can find the tribal layer on top of the surface that can prove it is due to the presence of tribal layer. As you can see here, the left hand side, that one is took by the optic microscope, and the right hand side is the laser scanning microscope, which shows the topography. And the point 1 point to the blue spot, actually it is pointing to the higher position in the pattern, and the P2 point to the ground region, actually it is pointing to the valley in the patterns. So let me explain that again, is that here the lower part is the laser texture structures, and after rubbing, then we found out that on top of the patterns we find these blue layers. And what are these blue layers? By using Raman spectroscopy, then we see that the P1, which is the blue point, actually it is pointing to iron sulfide, zinc sulfide, and also a P2O vibration. And on the other hand, the P2 point to the brown and also the valley points, it is showing a more pronounced iron oxide. So yes, we can see that the blue position on the top of the patterns is actually proved to be a ZDDP tribal layer by using Raman spectroscopy, and it is protecting the surface against further wear under the boundary lubrication. But here comes another question: why the laser textured patterns can enhance the growth of tribal layer? We made a contact simulation by using a boundary element method under a dry contact, and as you can see, here is the contact region by a cylinder roller to the bearing washer. Then we see the cross section here. Then we have the pressure in the pressure distribution, and actually you can see the pressure distribution. The green areas are the contact area in the cross pattern, the cross 30, and also the dimple. And we can see that if we see only the contact area, then yes, the both the dimple 200, the cross 9 and cross 30, they have less contact area compared to the reference, and the dimple 500 actually is very close to the contact area. And we know that the contact area, when a contact area is smaller, then we have a larger contact pressure. So we show here the proportion of contact pressure at the right hand side, that we classify the pressure with from 0 to 1 gigapascal, 1 to 3 gigapascal. It is because that according to the study from Goswami, they suggested that the pressure between 3 gigapascal to 7 gigapascal is beneficial for the growth of tribal layer. And as we can see within the samples cross 9 and cross 30, the pressure between 3 and 7 gigapascal is larger than the other samples. But the cross 9 has also a larger proportion in the pressure that larger than 7 and 9 gigapascal. And we can say that these pressure points that larger than 7 gigapascal is beyond the optimum pressure range, and actually it is harmful for the growth of trouble layer. So in the end, is the crust 30 that succeed to have a fully formed trouble layer on top of the surface, and then provide the protection function to decrease and reduce wear and also friction. Yep. Finally, we pick the crust 30, the best performance laser texture pattern on top of the ball bearing to test its fatigue lifetime. And you can see here the results. This plot, the blue line is the standard surface, and the red line is composed of the textured bearings. Then we can see that the life cycle, the load cycles increase actually from 1 to 3. So we increase the lifetime 3 times longer. And also, if you see the slope of these two lines is actually the same, we can say that the fatigue mechanism remains the same. So here comes to the conclusions. First, geometry and area density of the laser patterns alter the tribological performances. We actually created dimple and cross-like patterns on top of the surface of bearings, and all of them are capable to store lubricants into the surface, and when it's insufficient situation, the oil stored into the patterns will come out and play the role. And second is an increase of contact pressure enhances the formulation of ZDDP Tribofilm on the cross patterns. So by having the simulation, contact simulation, then we know that the increase from 3 gigapascal to 7 gigapascal is more on the crust 30 sample. And also by using Raman spectroscopy, we prove that on top of the patterns, we can see the fully formed trouble layer on it. And finally, by applying the crust 30 onto the ball bearings, and we can see that in the fatigue lifetime test, the lifetime of the bearing increases 3 times longer. So that's it. I hope you like it, and thank you very much.